Welcome to my talk using Android as OS for a single-purpose system. So my name is Martin. I work as a software developer for Cisco Systems here in Norway. This is my Twitter handle, and well, if you see this username anywhere, it's probably me. So if you want to get in touch, just do so. So in this talk, I'm going to start by explaining why I'm talking about this, and also why I am the one talking about this. I'm going to try and define a word I use, which is single-purpose system. What do I mean by that? And I'm going to go briefly through what Android is, before I go through the reasons why you would consider choosing Android to begin with. So we did use Android, and at some point we had some difficulties, so I go through a couple of those before I try to conclude on if using Android for single-purpose systems is a good idea or not. So why am I talking about this? Some history is important here. So I come from Cisco, previously Tandberg, and we have a quite mature code base with a mature application, as well as a mature operating system, a Linux distribution that we make in-house. We also have a cloud backend and quite a few devices that is running against these backends. I've been working in Cisco for 8 years now, so this is the environment I've been running most in. This also means that I've mainly been working on C++ based Linux applications. And I like to work, well, in user space, but closer to Linux APIs and messing around in that area. So at one point, I was involved in having our application being able to run on what is called a headless Android, and I'll come a bit back to what that would mean. But the larger part is in 2015, 2016, we acquired a company. And this company had a quite similar device to what we were already using that was already running Android. And it was running full Android with the Android application on top of it. So we took a small team from our 100 and something number of developers in that mature code base to help out in this new code base. And important to the story is in 2018, 2019, we switched over. We removed the Android code base and replaced it with our more mature code base. So today we don't have any Android running. So I'm telling you this because this, of course, colors my perspective on Android and what I feel about Android, and it's important for a lot of the points I'm going to make later on. So we have an existing code base, which is proven to run on several architectures on several devices. We mainly use a single application on top of a Linux distribution, and we also have custom hardware that is designed in-house in our offices. So what is this single-purpose system? And these are not single-purpose systems. These are Android devices. There's lots of other Android devices, like someone made an Android fridge, for instance, and there's Android Automotive coming. So it runs on a lot of different platforms and lots of different use cases, but the main thing that these things have in common is that they are running untrusted third-party applications like Twitter and Netflix and Angry Birds, like stuff that are not made by Google, who makes the operating system, and not made by the vendor of the hardware. They're from someone else. And these has to run on these devices. And to date, Google Play Store has a bit more than 2.7 million apps. So there's a lot of these untrusted applications. So there are security concerns with this. And what Android does is facilitating running these apps on basically any Android device. This, on the other hand, is what we make. It's a lot bigger than a normal phone, for instance, but it has a single purpose. The purpose of this thing here is collaboration. Now, that's a wide term, but what it does is you can call with it between two of these devices. You can share your screen. You can annotate on your screen share. Every feature that goes into this device is supposed to enhance the collaboration experience. So that's its purpose. It also doesn't run any untrusted applications. It runs applications either we make at Cisco or applications that we explicitly allow to run, like DHCP client. We're not going to write that ourselves. We're going to take something that is open source that we can use and allow that to run on our device. There's also a third thing, which is the user experience of this thing. We run a single application, and one of the reasons is we want a coherent user experience. So every single page or frame or whatever you see on this device is supposed to look like they belong together, which means we don't have the luxury of, for instance, using something that Google made, because the application won't look as like it's supposed to be in this ecosystem. So that's what I mean by a single purpose device. It has a single purpose, and in our case, we also define the experience ourselves. So what is Android in this case? Android for us is the Android open source project, also called AOSP. And it is based on a Linux kernel. What you do is you enable some Android features, and then you have a Android-capable Linux kernel. On top of that, you have the hardware abstraction layer. The hardware abstraction layer, or the HAL, provides a common interface to access resources like cameras, audio. And the way it does it, it provides an interface for the user, but it also provides an interface for the vendor to implement. So the vendor implements their own camera driver using the HAL interface. This gives two main benefits for the vendor. First off, it decreases turnaround time, because you can make a new implementation of this and push it to your device, and you can do that cycle quite rapidly. You also don't have the work to upstream it to the Linux kernel, which you might want to do if you make a Linux kernel driver. But what it also does is give you more freedom in licenses, because the HAL is BSD licensed. So you can, for instance, make a closed source driver without having to mess with any GPL code, as you would need to do in the Linux kernel. On top of that, we have native C and C++ libraries. Libraries you might expect on your standard embedded Linux box, like OpenGL, SQLite, a libc. And on the side there, you have an Android stack. And this is an Android runtime and the standard core libraries for Android. And this is where we get into for the application developer, really interesting parts of Android. You have a Java framework, an Android Java framework, as well as these managers. So the framework itself has a large API, and then you have these managers, which generally are applications running in the background, which you use to, for instance, get a hold of the camera image. So that manager is the one that actually grabs the camera, and every application goes through that manager. And on top of that, we have the system applications. There's quite a few system applications that is in the AOSP. As I said, we're not using those. We're actually just running on top of the API framework. If you want to, you can cut out the Java parts of this and run something that's more similar to an embedded Linux, use with C and C++ libraries, and running a headless Android. I'm not going to go too deep into that, but if you want to know more about that, Patricia Aas and Johan Herland had a talk about this in, I think it was 2015, making a headless Android system. There's a link at the end of the slides, so you can take a picture and look at that. It's quite good. So, what differences does Android and Linux have? Well, Android is a set of libraries and applications and tools on top of a Linux kernel. So in that sense, it's a Linux distribution. But it's not a standard Linux distribution. There are quite a few changes. For instance, Android has to run on very low power devices, like you have watches that runs Android. So Android has made their own power management system that replaces, for instance, ACPI. It uses its own file system layout. So if you ever used ADB to look into an actual Android device, the file system layout does not follow the file system hierarchy standard that most distributions follow in some way. So it's quite different file system layout. And the purpose of Android is to isolate applications running on Android. So you have two applications that you don't trust. And the goal of Android is to make sure that application A can't interfere with application B, which also means it can't read secrets or configuration files, or it shouldn't really care that application B is there. So that's the purpose of actually having Android. There's also some other changes or differences. For instance, Android and the AOSP prefers Apache 2 licenses, while a general normal embedded Linux system has a lot of GPL that is basically banned in the AOSP, because they don't want to give the vendor the challenge of having to make their patches available. They want to give the vendor full freedom to do whatever they want without any constraints. So you'll find a lot of Apache 2, BSD, and MIT licenses, and the only thing that is actual GPL there is the Linux kernel itself. It also uses Bionic as a C library instead of the more popular in embedded Linux world glibc or eglibc. So generally, Android is a full platform. You get a package which is a platform with very limited choices of components. While with embedded Linux, you can pick and choose more what you actually want. So there's pros and cons of both of these. As I mentioned, there's a difference in C libraries. So I'm going to try and compare a bit Bionic versus glibc. Because Bionic is developed for Android. glibc is used most Linux distributions, and there are some differences here. So if you're used to glibc, you might get into some of the worst corners of Bionic. So a C library is supposed to implement the C library, POSIX libraries, and Linux APIs if you're running on Linux. With Bionic, they aim to implement all of C11, all of POSIX, except where they don't agree. But on the Linux API side, they have been implementing what is needed for the Java runtime, and also what customers complain about when it's missing. So they don't aim to have a full implementation of the Linux APIs. Bionic is also BSD license, which is why it was made. Most of it is taken from OpenBSD. But they have very different design goals. So Bionic is aiming to have a very small memory footprint, as well as being quite fast on low clock frequencies. While glibc is aiming to be a complete C library. They need backwards compatibility, and they want to be compliant with standards. So these two different goals might have some implication later on. So why would you choose Android to begin with? One of the reasons are hardware independence. In theory, you can use any Android device to test any Android application, as long as it's built for that target. The reason is because of the HAL, for instance, which gives you a standard API to get actual hardware resources. If you have custom hardware, you might need to abstract away some of those so you actually can run on other hardware. But in the end, you probably, with an effort, you might get into something where you can actually just use your Android phone to test your application instead of like really expensive or really large or scarce hardware. It also might mean that you can start a bit earlier with actually implementing your application because you don't need the actual hardware yet. At some point you do, but you might not need it right now. There's also an issue with vendor support, because you might choose a vendor which only provides you with Android drivers. Their board support package is Android. One of the reasons to do that is because they want to target the phone market. And the phone market is huge, so if you get a small pie, or a small piece of that pie, you can make serious money. The reasons this is an issue, or the reasons why this means you probably can't run Linux, is because you have binary drivers. These binary drivers are compiled for Android and not for Linux, which basically means you have a dependency on Bionic, which you don't necessarily have otherwise. If you really want to run Linux, you can do something like running headless Android, or you can do something like adding a compatibility layer like libhybris, which is also talked about by Patricia and Henrik and Johan in making a headless Android system. So I'm not going to go into that, but if you want to do something like that, please watch that. The tooling of Android is very good. So Android has an enormous amount of tools, and most of them are packaged neatly into Android Studio, which is the IDE of choice when you work on Android. It provides you out-of-the-box stuff like remote debugging, fetching logs, a few things that you probably expect. But it also gives you the opportunity to fire up a virtual device using QEMU. And in the Android Studio package, there's a lot of predefined phones that you can actually use. And if you find some that's quite close to your hardware, you can just use that and run your application without even having a phone. You can emulate it all on your host machine. You can also make your own Android and push it into Android Studio and have that available as a virtual device. It also gives you stuff like remote monitoring, visualization of hardware usage, performance metrics. And if you're a UI person, you also get a very good UI visualization tool directly in the editor. So you can see how your UI looks and behaves without ever touching anything except having it in your editor, which is pretty nice. Android also has a huge API. They have APIs to probe for hardware information, which will go through the HAL again. So you can expect those to be available for every single device you're running on. It has APIs to listen to property changes or to listen to what is called intents, which is another application stating that, hey, I want you to do something, and then you can do that for them. And it has a large API to configure the whole system, as well as a really good and really big UI API. And the UI API is not only big, but it's also very extendable. So if you're making a UI and you're missing, components, chances are you have already someone on the internet that has made that component, and you can grab that and use it. Like I said earlier, there's more than 2.7 million Android applications. That means there's a lot of people out there that knows Android. If you're, for instance, recruiting, that's a good thing. On a more regular basis for you as a developer, it creates a big community. And Android has a big community both on the application side and on the AOSP side. So if you ask something on Stack Overflow, there's a lot of people that probably knows the answer. I can help you out. Some of the answers you get and find are actually really good. On embedded Linux, that might be a bit harder because you have way more choice. You can set up your distribution as you want it. So when someone answers, their environment might be different than your environment. If you're on Android, your environment are more or less the same. But like I said, we ended up removing Android. Not all of them are Android's fault, but we did have some issues. So what are the difficulties we actually ended up having with Android? One of them is API behavior. Generally, the Android APIs are very well documented. There's a lot of documentation, and most of the time it's correct, except for when it's not. When you're touching the APIs that are really not meant to be used for standard applications. For instance, the AOSP comes with a settings application. You're not really meant to do the settings yourself. So it feels like those APIs have had less thought. I worked a lot on getting Wi-Fi to work on our system, and one of the things there is the API is very designed around VPA supplicant, which is the underlying model. Which means if you want to get all the Wi-Fi endpoints, you want to get a list of these. First, you have to tell the driver to scan for Wi-Fi networks, which gives you a callback. But this callback is empty. You would probably expect that to contain the actual endpoints, but it only tells you, hey, I'm done. So the next step is to do another asynchronous call to actually get the devices. It's not a big deal, but it's kind of annoying when the rest of the API seems very well thought out. But worse than that is that with the Google documentation, you can most of the time trust it until you suddenly can't. Because the APIs for actually getting the list of devices states that this will always return a list of devices, which means if there are no devices, you will get an empty list. And this makes sense. The problem is when it lies and suddenly returns null, which for obvious reasons you will never see until you push this to production and starts crashing. The platform itself is also designed around certain use cases. The main use cases are phone. And the APIs are designed around the fact that most people are making a phone using Android. So certain APIs are missing, certain APIs that we really need. there's no support for HDMI in the AOSP. And as I said, we can share our screen, so we obviously need support for HDMI. The same goes for Ethernet. Like, no phone uses Ethernet. Why would they? Use Wi-Fi. There's also more obscure APIs, like the Cisco Discovery Protocol, which is that we use to figure out if the customer wants their video devices to be in a separate network. That's an important feature for us, but of course not something you would bother writing in your phone. There's also some DHCP codes that we use that are missing. And there's probably a lot more small stuff that we had to make ourselves. Because if they're not in Android, you have two choices. You can either use extend the AOSP, or you can do something else, which is going into C++ and writing more kernel close code. And I'll get a bit back to that. One of the things we were kind of missing, it wasn't missing, it was limited, was the HTTP proxy. So the proxy support in Android is very limited. You can set up a global proxy. You can say that every single HTTP request from this device is supposed to go to this proxy. That is fine until you have lots of devices out in the market from the same company, which also supports other ways of doing proxy, like PAC, which is Proxy Automated Configuration, something like that. What that is a JavaScript file, which is interpreted. It sends in the host and the URI that you want to reach. And then that JavaScript file is used to evaluate what proxy you're supposed to go to. So you can say that these URIs goes to this proxy, these URIs go to this proxy, these internal URIs goes just directly, and between 5 and 6, no one's gonna reach the internet, so we just block everything. Stuff like that is possible with this PAC script thing, and it's not supported at all on Android. For us, we had that solved already in our more mature system, but these two ways of doing it was not compatible. It was not compatible with Android, so we had to solve it again in a different way. So the solution was to set up a proxy resolver with the perfect name Proxy, because it proxies to a proxy. And we set the global proxy to go to the port of this proxy resolver. So it just went to a local port, and that one did all the figuring out where to send your HTTP request, and it was configured from the outside. So if you had a PAC file, it would resolve the PAC file. If you had just set up a global proxy, it would just send everything to the global proxy. But that had to be solved by adding basically a new API to the AOSP for us. There's also a second part of this, which is actually discovering where this PAC file is, which is called vpad, and that we had to also add, but then we could add that directly in the application. Android has some hardware information. You can grab some of it. You can also use the hardware, but some of the hardware information is pretty limited or completely missing. So for instance, if you want to take a MAC address and use that as input to generate some unique identifier for all your system that is out in the world, then Android has an API for this. It's a very easy API to get the MAC address. The problem is, this is returned. Regardless of device, regardless of vendor, the API always returns this, which is pretty useless to actually use as input for something that's supposed to be unique. So again, we had to extend the AOSP to get a proper API to actually get the MAC address. And it's a good reason actually for Android to do this, because a normal device, a normal Android application is not supposed to know anything unique about the device it's running on. You're not supposed to be able to identify a device and via that identify a person. So it's sensible that the API doesn't return it, but then again we need it because we had to be compatible with our other devices. Yes?
Why do they have the API?
At one point it returned something sensible,
Okay.
and then they stopped that. They figured out this was a bad idea. There's also other things that are completely missing. So we want to be able to tell a customer that, hey, we see that your device here is running really, really warm. Can you please ship it back to us so we can send you a new one? The problem is there are no temperature sensor information that you can get from Android. So again, this is stuff we had to make ourselves, which means again, extending the AOSP and working around actual security measures in Android. And then we get to the Java Native Interface, or JNI. I briefly said that one way you could get, for instance, HDMI hot plugging implemented is by writing it in C or C++. To do that in your application, you have to use the Java Native Interface, JNI. And if you go to Android conference, you will hear time and time again that C++ is extremely scary. It is super hard and don't do it. I do not believe that the reason is that C++ is as hard. Like, there are corners of C++, but it is doable. I also don't think it's necessarily because these are bad programmers. I think a lot of the reason is this, the Java Native Interface. The interface itself is very verbose and hard to do right. There's also these fun caveats. In the AOSP there's comments. Some of these comments states that holding a pointer to Java memory while in native code, meaning C or C++, is very dangerous. Because Java is allowed to move your memory to a new location. Which means the next time you call this and you try and dereference this pointer, you're suddenly in undefined behavior land, which is not somewhere you want to be. So the AOSP tells us this, and then they tell us why they're doing it right and why their solution to it really works. Again, you push stuff to production and it turns out the AOSP is wrong because you crash inside of their code. Which brings us to backtraces. Especially backtraces when you go through the JNI. Because if you crash in native code, you will not get a Java backtrace. You will get a C++ native backtrace. And that does not know where you were calling your native API from. So you have no idea where in your Java code your call came from. If the reason you're crashing is that you're using the interface of the AOSP wrong, you have no idea where your call came from. That means hours and hours and days and possibly weeks of debugging, because of course you're calling this API from lots of places. Because they only do this technique in hotpots. So you call it a lot of times and you crash and you have no idea where you're misbehaving. This is not fun at all to have to be in. And sometimes you might want to upgrade your AOSP. Because the AOSP contains all of your libraries, or at least most of your libraries. You can link in new ones in your APK, in your application, and push them up. But most of your libraries, most of your applications are part of the AOSP. And in the case of Android, you have Google, which makes the AOSP, and then you have a vendor. And what's very important to understand about AOSP is that it is open source, but it's not open development. And with open development means that there are key parts of the AOSP that are developed behind closed doors at Google. And every now and then, Google thinks that, okay, it's time for a new Android release. Then you get the code, and you get all the code. So you have no idea what the changes are while they're working on them. You just suddenly get them. And when they dump all this code, your vendor has to take them. And they have to rebase their changes. And they have to do their changes to their closed source drivers. And when they're done with that work, which is probably quite long, you get the vendor AOSP. Which means you can now rebase your patches on top of the AOSP. But this creates a chain of dependencies which is longer than what you have if you do a standard embedded Linux system, where you can say, I want to update SQLite now. You can update the components that you want to. You don't have that freedom in the AOSP without shooting yourself in the foot. Because you can update a single part if you want to, but that's a manual job and it will not be compatible. There's also another very scary thing about this. Because your vendor might decide that they're done with Android for this chip. And then you're stuck. Because you can't update it because they have binary drivers that you depend on that depend on a previous Android version. Which means if the vendor stops, you're stuck. Then we get to the Android toolchain. So the Android toolchain is the compiler and standard libraries that Google decides that you're supposed to use when you write native code in Android. These are provided by Google, and you have very little choice in changing this. Of course, you can add new libraries on the side, but they then have to be compiled for Android, and you have to link them in so they work together. But this, among other things, contains Bionic, or Bionic headers at least, because that's what you use on Android. And Bionic has some limitations. For instance, Bionic has a very limited pthread support. It supports pthreads, but it's limited. One of the things it doesn't support that you really have to work to get working is real-time scheduling. If you want that, then yeah, that might be an issue. So why would you want that? If you're, for instance, making, let's say, you want a thread running audio that needs to tick every now and then and do its work on regular intervals, like some of us might want. So you can define some thread priorities, but you cannot say that this thread is real-time. You cannot guarantee that this thread will get the actual runtime it needs. It also has hard-coded users, which might be a bigger issue. Because that means if you, for instance, have a way to add users in your device, then Android really won't help you. You will have to make your own user model and your own permissions and do that in the application itself. You cannot really use the Linux user and group policies to solve this, because all of the users on Android are hard-coded. You cannot make new users, which is fun. So the big question, should I use Android? Let's just take a quick summary. So on Android, you have really good tooling. You have a lot of people and a big community, which is helpful. You have UI APIs, which are really good. I'm not a UI person, but I could even do something in the UI with this. And given that you design stuff correctly, you will have hardware independence, which is all good things. On the negative side, it includes a vendor dependency, a very hard vendor dependency that you probably didn't have if you didn't use Android. If you need some information of hardware, especially if you use custom hardware like we do, you might need to work around Android to actually get that information or do something with that hardware. The APIs are very phone specific. So again, custom hardware, other use cases than phones, you might need to work around Android again. And you might have gathered that I'm not a big fan of Bionic during this speech, so yeah. But the answer is maybe. Kind of depends. For us that already has a mature operating system and a mature application that has been proven to be able to run on multiple hardware platforms, multiple different types of solutions, then no, I wouldn't have us use Android ever again on our systems. If your device is more general and what you want to do is install third-party applications on it, yes, this is exactly what Android was made for. This is what it solves for you. So if you make a general device that is not a single-purpose device, definitely use Android. If I was on a greenfield project and I could choose a vendor which provided both an Android and a Linux type solution for me. If I really had a choice, I would personally go for instance, Yocto. And Chris here had a had a workshop on that earlier this week. So that is, they made it a lot easier to get going on embedded Linux. And given my experience and my interests, I would rather go with Yocto. I promised you some resources. I'll just leave this up for 30 seconds or so, and while you can take a picture. So this one is really worth a watch, especially if you want to do something like headless Android. And then the last phone goes down soon. So what questions do you have for me?